Good evening, everybody. Welcome to day one on week 12 of the semester. Remember that this week we have our exam number 3. The study guide has been posted, so you can look at the major topics that we have discussed for the material on the exam, which is going to be the very last section of chapter 5, then all of chapter 6, and then the majority of chapter 7, up until the concept of hydrogenation. So understand that section 7.6 is not in exam 3. So let's get started talking about attractive forces, but specifically in cell membranes. Now, it is important to note that throughout chapter 7, we have been talking about the different attractive forces. We have talked about the structures that are present in membranes, some of the structures that are in membranes. But what I want to point out is that when it comes to attractive forces in cell membranes, it is important to remember some of the concepts that you might have explored in biology. So what we see here in our diagram, this represents a cell similar to our animal cells. Our animal cells are composed of different organelles. Organelles are just going to be membrane-bound components inside the cell. As you can see here, is illustrating 3 major organelles. We have the nucleus, which is represented here by this gray figure. Then we have the cytoplasm, which is going to be that fluid-like environment inside of the cell. And then we can see other components there. And then lastly, all that area that is shown in green is what is the plasma membrane, okay? So why is the plasma membrane so important? In the plasma membrane, it is important to note that it is made out of lipids, which is one of the things that we learned about last week. We can see that in that green area, why it looks mostly green, is because it is made out of specifically a phospholipid, or in other words, a phospho or a glycerol phospholipid. To remind you how chemically a glycerol phospholipid looks like, if we go back into section 7.5, the glycerol phospholipids is going to be specifically this third one. So a glycerol phospholipid has a glycerol molecule connected to 2 fatty acids, and is also connected to a phosphate group, and is connected to an amino alcohol, okay? All of that is one molecule of glycerol phospholipids. Traditionally, whenever we are drawing a glycerol phospholipid, understand that because of structurally and the different functional groups that is present in it, we draw a circle followed by or connected to 2 tails, okay? So if I try to utilize colors to represent what does the circle mean and what do the 2 tails mean? So the fatty acids are going to be the tails, okay? And then the circle that we see is going to be specifically this area of the molecule, that phosphate and that amino alcohol. That's what is represented by that circle, okay? So understand that when it comes to this, because the fatty acid tails are long and nonpolar, this area of your glycerol phospholipid is considered to be a nonpolar. If it's nonpolar, it's going to be hydrophobic. In other words, it's going to be afraid of water, okay? The area of the phosphate and the amino alcohol, this is the polar portion of my glycerol phospholipid. Taking that into consideration, that means that this is hydrophilic. Okay. So when we go back and we look at the structure of the cell membrane, we can see that what I highlighted in pink is going to be that green area. And then the two tails, which is where the fatty acid non-polar portion is going to be the yellow, okay? But let's understand that even though the majority of what we see here is going to be this glycerol phospholipid, there are other important components that are present in cell membranes. Cell membranes also have carbohydrate chains. I remember when I was taking biochemistry that our professors will always say, you know what? Animal cells look like M&Ms because they have sugars in it, okay? In later chapters, we are going to learn what proteins are, but just to introduce it to you, proteins are actually biomolecules made of amino acids. Lastly, we also have another type of lipid, which you can see here. Let me just highlight it for you. Glycerol, which is going to be this structure right here that I highlighted in blue. Cholesterol is a type of lipid, okay? And when it comes to the types of lipid, and again, going back to this structure, cholesterol is actually considered a steroid because it has this motif of 6-member ring, 6-member ring, 6-member ring, 5-member ring. So cholesterol, which is another type of lipid, is the most common steroid in the human body. It is very important because, as you can see here, cholesterol is going to be part of the structure of the cell membrane, which is going to be protecting the cell. And we're going to see in chapter 8 how it actually mediates things coming inside of the cell or actually leaving the cell. And cholesterol is also important because it gives rise to other important biomolecules that include sex hormones, it includes fat-soluble vitamins. So understand that cholesterol is actually very important in the human body. Now, whenever we have to think about attractive forces in the cell membrane, understand that when we rationalize the attractive forces that are present here, okay? And if we go back and focus into the different components, okay? Because in the middle, okay, of your cell membrane, there's going to be hydrophobic areas. In other words, non-polar areas. We can rationalize that the reason why the hydrophobic regions of those two layers of glycerol phospholipids that we have in our cell membrane is due to dispersion forces. Again, from the fact that what is interacting there is going to be non-polar molecules. On the other hand, when we look at what is happening outside of the cell, meaning the polar regions, that are going to be in that green area that you can see on top, and you can see also in the bottom because there's two layers of them. There is interesting because the interaction that may happen with water or with other polar substances may be mediated by hydrogen bonding or dipole-dipole attractions, okay? Sometimes we could even see how some attractive forces that are also observed there, like on the surface or inside of the cell, could be ion dipole, but it depends on the different cases of what we see. Now, in addition to understand that cell membranes, because they're very diverse in their compositions, we usually talk about them in terms of the fluidity that a cell membrane has. So whenever we're describing a cell membrane, we always talk about the fluid mosaic model. And as you can see, the fluid mosaic model explains the structural components of biological membranes, okay? As I mentioned a few moments ago, and you can see on the first bullet point, the lipid bilayer, remember, is 2 layers of that glycerophospholipid that are going to be interacting via the tails, are going to contain proteins, carbohydrates, cholesterol, in addition to the glycerophospholipid. Now, the reason why we mostly see the cell membrane as something that is fluid is because specifically those tails that we have here in terms of the structure are going to be from unsaturated fatty acids, okay? And since they are unsaturated fatty acids, instead of being rigid like a saturated fatty acid, they're more fluid-like. We learned previously in this chapter how things that are unsaturated, because they cannot stack well, okay, because they have less dispersion forces compared to saturated, understand that overall, that's where the fluidity comes from. The term mosaic comes from specifically the diverse components that we have in the cell membranes. So again, when it comes to attractive forces, specifically that have to do with the cell membrane, remember that in the area that is inside where the tails are interacting with one another, this area, mostly what we are observing is dispersion forces interacting with one another, okay? Outside of the cell, where we have that red area in this illustration, that is going to depend in which molecules they're interacting with. We could see dipole-dipole attractions, we could see ion dipole attractions. It depends on what substances we're interacting with. But this is the end of chapter 7. Now we are going to move on to the concepts of chapter 8. So when it comes to the concepts of chapter 8, specifically, we are going to learn about what are solutions, okay? And the term solutions is another word that we can utilize for homogeneous mixtures. Earlier in the semester, we learned about the different types of matter that are there, depending on their chemical composition. We learned about pure substances, and we learned about mixtures, and there are homogeneous mixtures and heterogeneous mixtures. So understand that whenever we are talking about specifically a homogeneous mixture, is the same thing as saying a solution, okay? So how are solutions made? Well, solutions are made by several components, okay? Let's first establish that when it comes to the components of a solution, we have 2 main things that it must be present. The first one is the solvent, And the solvent is going to be the substance that is found in a larger amount. And whenever we have a solution, we are going to have specifically one solvent, okay? Then that solvent, we need to put another compound in. And that compound that is present in lesser amount or in a smaller amount, that is known as the solute, okay? And when it comes to a mixture, you can have one or more solutes in a solution, okay? In the right corner of the slides, we have a solution that is being formed in which we are combining salt and water. We can see that the water is the substance in larger amount, in other words, the solvent in this solution, while the salt is the substance that is present in lesser amount, and that's why it's known as a solute. The reasoning why solutions can be made is because overall, what's going to happen is that the interaction between the molecules of the solute and the solvent are going to be greater than the solute by itself and the solvent by itself. So because of that, because that solute want to be dissolved in that solvent, that's how we make a solution. Now, when it comes to the different types of solutions out there, we have unsaturated solutions and we can have a saturated solution. So what is an unsaturated solution? An unsaturated solution is going to contain less than the maximum amount of solute that can be dissolved in a particular amount of solvent. So what does that mean overall? That since there is less solute that the solvent can hold, we can dissolve more solute in that solvent. And you can see here in the image on the left, this is just illustrating how we have specifically a unsaturated solution. Let's now look at the other type of solution, which is a saturated solution. A saturated solution, on the other hand, contains the maximum amount of solute that can dissolve in that particular solvent. Now, understand that sometimes when we have saturated solutions, you can actually see undissolved solute in the bottom of the container, okay? So in addition to this, there's one more. We can also have what is called a super saturated solution. And what is a supersaturated solution? It contains more than the maximum amount of solute that can dissolve in a particular solvent. And maybe some of you will be like, what is a supersaturated solution? Let me give you the classic example of a supersaturated solution, okay? Put a 1 in the chat if you like Cane's sweet tea. Ooh, I see a 1. Maybe you don't like it, but maybe you heard of sweet tea. Okay. Now, put a 2 in the chat if you have heard of, you know how to make sweet tea. Ooh, I have a few people that know either how to make it or they've heard how to make sweet tea, okay? Now, One of the things that is utilized to make supersaturated solutions, specifically in sweet tea, if it's made appropriately, is that heat is used to create this type of solution, okay? Now, according to my background, living in Texas for 7 years, when it comes to making sweet tea, or the way that I learned while I was doing my studies when I was in grad school in Texas, is that you take water, okay, and then you must warm up that water. Then you add sugar, and then you make, you keep on adding sugar. It's up to the point, at least the way that I've learned it, correct me if I'm wrong, you guys, that you make kind of like a simple syrup. And then when you still have that sugar drink or that simple syrup, then you steep the tea in it. At least that's how I learned how to make it. I do not make it, I don't drink it, but it's super delicious, right? Now, what happens in supersaturated solutions? Supersaturated solutions, sometimes, if you add crystals of the solute that you utilize to create that supersaturated solution, you can actually crystallize, okay, the solute out. So for example, for those of you that may enjoy rock candy, that's how it's made. You make a supersaturated solution, and then you can actually put in whatever the popsicle stick or the wood stick or whatever stick you're going to place the rock candy. If you put a few pieces of the sugar in it, then it crystallizes on the lollipop, and that's how you make rock candy. So as you can see, supersaturated solutions do exist, but the key is that it contains more than the maximum amount of solute because heat is utilized in order to create such solution, okay? Now, understand that solutions, it is important to note that they come in all 3 states of matter. Most of the time, people think that solutions can only be liquid, but they're not. We can have gas solutions, we can have liquid solutions, and we can have solid solutions. So again, solutions exist in all 3 states of matter, okay? So let me give you guys an example of a gas solution. So if we look at this table right here, we can see that one example of a gas solution is the air we breathe, okay? When it comes to air, and you can see the pie chart that is on the right side of the slide, air is actually made mostly of nitrogen. Then the main solute that is present in air is oxygen, but there's other gases in there. There's argon, there's carbon dioxide, there's steam, okay? But you can see that because there are different gases present in air, that is known as a gas solution. Now, in order for something to be considered a gas solution, both your solute and your solvent needs to be found in gas form. So that's why we see it here. We can also have liquid solutions, which is the one that we are most familiar with. When it comes to liquid solutions, understand that in liquid solutions, your solute can be gas, it can be liquid, it could be solid. The main thing that makes a solution liquid is going to be that your solvent is in liquid form. So we can see here that we can have a gas in a liquid. So for example, when you take any carbonated drink, okay, that's because CO2 has been placed in that liquid, we can have a liquid-liquid solution. So for example, when you utilize vinegar, right? Vinegar is this compound that is called acetic acid, which is a carboxylic acid that is placed in water. That's why you see the bottle of vinegar that I put as a picture on the right side. We also can have solids and liquids. So seawater, as you can see, sodium chloride can be placed in water, but it is important to note, and we're going to explore soon, how not all molecules are actually soluble in water. So for example, iodine solid is soluble in ethanol, okay? Lastly, we have a solid solution. And when we have a solid solution, understand that our solute and our solvent must be solid. Two examples that I have here of a solid solution include brass and steel. Brass and steel, as you can see, the solute and the solvent are going to be elements that are metal. But it is important to note that in these, okay, this zinc and copper in the case of brass, or carbon and iron in the case of steel, are not chemically linked to one another. They're just physically mixed, okay? Does anybody remember, and let's put it in the chat, what is the term that we utilize for whenever we have metal elements that we combine to make a homogeneous mixture? This was from about 3 months ago when we learned about this. Anybody remembers? What do we call these solid solutions? Let me remind you guys, these are called alloys. Now, it is important to note that when it comes to solutions, we can have different mixtures out there, and the ones that are called solutions are going to be the ones that are homogeneous mixtures, okay? We can also have mixtures out there that, even though we explore them in everyday life, people actually assume that they're solutions, but they're not. So, for example, suspensions, okay, which is the last column that you see here, that is not a homogeneous mixture, okay? Suspensions are actually a heterogeneous mixture. Solutions, remember that they are homogeneous mixtures. So a solution is not a suspension, okay? Just because sometimes people use them in everyday life interchangeably, but they shouldn't, because they're not expressing the same thing, okay? Now, why is a suspension considered a heterogeneous mixture? Well, because you can actually see the different components that it has. So for example, look at the example that we have on the table. We have muddy water, okay? Now, it is important that for the next exam, for exam 4, you know the different properties that solutions, suspensions, and colloids have, okay? Now, we have something right in the middle, a colloid, okay? Now, colloids are actually special because colloids are actually families of the homogeneous mixtures. But the difference between a solution and a colloid, as you can see, is the particle size, okay? While in a solution, the particle size of the solute in that solvent is less than 1 nanometer, for a colloid, it can go from 1 to 100 nanometers, okay? you can see that the particle size for a suspension is actually more than 100 nanometers. When it comes to how do they look to our eyes, many solutions look clear, okay? Now, on the other hand, many colloids actually look cloudy, but it's because of the particle sizes that are present in that type of homogeneous mixtures. Suspensions, on the other hand, similar to colloids, they appear to be cloudy. Now, solutions and colloids cannot separate. Suspensions do separate, okay? And it actually settles. Now, when it comes to can you filter a solution, a colloid, or a suspension, you can see that specifically a solution and a colloid can be passed through filter paper, but a suspension, you can actually separate the particles because they are going to get stuck to the filter paper. Lastly, we're going to talk about how can light pass through any of these three different type of mixtures. Well, you can see that the only one that you can pass light through is going to be the solution. The colloid scatters the light, and then the light can not actually pass through a suspension. And in the last part, we can see examples of solutions, colloids, and suspensions. So this is just to illustrate of the different types of mixtures that are out there. Okay. Now, in section 8.2, in the book, there's a discussion about the formations of a solution. Now, this concept we already explored in chapter 7, and we understand, just to remind you, that there is a rule of thumb of how a solution is made. It is basically the term like dissolves like. And in like dissolves like, we need to remind ourselves that all of this is driven by attractive forces. So attractive forces is what indeed explains why is it that polar molecules dissolve in polar solvents. Similarly, if you have a nonpolar molecule, it's going to dissolve in a nonpolar solvent. Now, if your molecule, as you can see in the third bullet point, has both polar and nonpolar parts, let's understand that it depends on the amount of nonpolar versus polar character. And we explored earlier that, for example, in this fatty acid, oleic acid, because the nonpolar portion, which is all of this, is much larger than the polar side, this molecule is overall nonpolar. So when we have a molecule that is overall nonpolar, we understand that most likely the correct solvent that they need in order for them to create a solution is going to be a nonpolar molecule. Now, it is important to note, as we saw a few moments ago, that when it comes to liquid solutions, one of the main solvent, if not the most important one, is water. Okay? Water is the most common solvent in nature. It is so common that when we look at the human body, 72, on average, 72% of the human body is made out of water. So what does that mean? That whenever molecules in our body need to be interacting with something, most likely they're going to be interacting with water. Now, when it comes to water, it is important to note that water is a polar molecule. So since water is a polar molecule, understand that when things are trying to interact with water, then they're going to do it through ion-dipole attractions, hydrogen bonding, dipole-dipole attractions. And sometimes if something that is non-polar, is exposed to water, is going to basically hide away because it's afraid of water. Okay. And later chapters, we're going to see how that actually leads to structural components in some biomolecules that we will be exploring. Now, I mentioned a few moments ago that when it comes to ionic compounds, not all ionic compounds are actually soluble in water. And since not all ionic compounds are soluble in water, sometimes we have, in specifically double replacement reactions, the formation of a solid. We can see in the right side of the slide, two ionic compounds that are soluble in water. So here we have potassium iodide, which is what is entering right here. And we also have lead 2 nitrate. And you can see that lead 2 nitrate is basically what is inside. Okay, all of that is lead 2 nitrate. Now, you see that they have the symbol AQ. What does AQ stand for? Let's put it in the chat. What does AQ stand for? Great job. Aqueous. And remember that aqueous simply means that this is going to be a compound that dissolves in water. Okay. So it was combined with water and it made a solution. Now, one of the things that we can see that when these two aqueous solutions, meaning the potassium iodide and that lead 2 nitrate were combined, all of a sudden, we can observe that specifically this yellow compound is made. And this specifically is going to be lead 2 iodide. Okay. And we can see that it is formed and it has a particular color. And now it's going to have the symbol S. S stands for solid. Okay. You may be wondering, well, I can see that there's another compound that is there, which is the potassium nitrate. Now, understand that in this reaction, that KNO3 is also in the solution because it is aqueous. It's just that since it's clear and colorless, we cannot see it, but it's in there, okay? So why are solubility rules important? Solubility rules tell you about the ability of certain compounds to be soluble in water. And in double replacement reactions, it is particularly important to note, do you form a precipitate or not? So I was looking at a TV show the other day about paramedics, and it was interesting to see that they actually illustrated a double replacement reaction while they were treating a patient. Sometimes when you have different compounds that are coming in intravenous bags, specifically, they tried to illustrate how this person was not careful with the two aqueous solutions that were in the IV bags. And then when they combined them, all of a sudden they clogged the line, and then their patient was not receiving the medication. And it's because overall, the double replacement reaction that occurred by combining two things that were aqueous, that's what clogged the line, okay? Now, when it comes to solubility rules, I'm going to hold you guys responsible for the solubility rules that we have specifically here in this table. So I want to at least go over the different solubility rules, okay, and explain how this table must be read. Then we are going to go through problems here to understand how we can predict the products for a double replacement reaction. And we can see which of the products is actually going to be the one that precipitates. So let me just cut and paste the table so we can discuss the solubility rules. So we know how to determine. Let me do it in a separate sheet so I can take more notes. Okay, so this is my table for solubility rules. I'm going to number each one of the different rows that we see here. So this is going to be number 1, this is number 2, this is number 3, 4, 5, and then these guys, I'm going to put them together, and that's going to be number 6. This is how you read a solubility rule table, which is, let me just write it in the slides. You need for exam 4. So this is how solubility rules work. The first row, it actually says an ionic solid is soluble if it contains lithium, sodium, potassium, or ammonium. We can see that next to those, it says the word none. So for rule number 1 and number 2, basically it means that any anion paired with these cations is soluble in water. So we label it aqueous. Let's go through rule number 3. We have nitrate and we have acetate. So if an ionic solid has nitrate or acetate, let's understand that they're going to be soluble. Since next to nitrate and acetate, we see the word none. What that means is that any cation paired with nitrate and acetate is soluble in water. So we label it aqueous, AQ, okay? Put a 1 in the chat if so far rules 1, 2, or 3 you are following. I just want to make sure that I haven't lost anybody in rules 1, 2, and 3. Just put a 1 in the chat. I have 3 more students. Let's move on to number 4. In number 4, it says that if a compound contains chloride, bromide, or iodide, it's going to be soluble in water. Now we see that next to it, we have a list of cations. Silver, lead 2, mercury 1. So what this means is that any cation other than silver, lead 2, mercury 1 will be soluble in water. If chloride, bromide, or iodide are paired with silver ion, lead 2 ion, or mercury ion, they will be insoluble in water. A compound insoluble in water is labeled solid. That means that we put an S by it, okay? So in rule number 4, hey, chloride, bromide, and iodide will be soluble unless you pair them with silver, lead 2, or mercury ions, okay? Let's now move on to rule number 5. Which is sulfate. You can see that sulfate, if it's present in the molecule, hey, it's going to be soluble. But notice that sulfate has some cations that shouldn't be present if you want it to be soluble, okay? So those cations are barium, lead 2, calcium, or strontium. So when it comes to it, sulfate ion is soluble in water unless it's paired with barium ion, lead 2 ion, calcium ion, or strontium ion. So what that means is when sulfate is paired with any of those four, it forms a solid. So that's why we will label it S. Okay. Let's go through the last one, which is rule 6. As you can see, carbonate, sulfide, phosphate, and hydroxide is insoluble in water. Okay. Carbonate ion, sulfide ion, phosphate ion, and hydroxide ions paired with cations form solids unless the cations are in group 1 and 2. What I mean with group 1 and 2 is lithium, sodium, potassium, ammonium. Then they form compounds that are soluble in water, meaning aqueous. Okay? So again, these are solubility rules. It actually explains how these cations and anions are going to behave in the presence of water. And the best way that we can actually use this as an application is going to be in double replacement reactions. So let's explore now how, if we're given a double replacement reaction, we can predict the product and determine if they're aqueous or if the product will be a solid. So let's actually look at the following double replacement reactions, okay? I'm going to walk you guys through the first one. As you can see here, we have AlI3, okay? If I go to my solubility rules, because AlI3 is iodine paired with a cation that is not silver, lead, or mercury. That means that AlI3 is an aqueous. It can form an aqueous solution, okay? Here we have HgCl2. We look at our solubility rules. Cl is paired with Cl2. Is that aqueous or solid? I don't see any respond on the chat. Which part do I have to repeat? No problem. So ALI3 is an aqueous solution. What about HgCl2? Is that aqueous or solid? Again, based on the solubility rules. I only see one response. There's 7 of you out there. I want to make sure that you guys get this. This is a concept that we need to explore and I see that you guys put aqueous. Let's look at rule number 4. I see that one student see it, but I need all 7 of you guys. So rule number 4 says that if you have chlorine, bromine, and iodine, you're soluble unless you're paired with Hg,Pb2+, or mercury ion. So when it comes to this reaction, this is already a solid. So when it comes to double replacement reactions, both reactants need to be aqueous. Let's move on to number 2 and number 3. Let me see that people get this. Let's look at the first one, calcium acetate. Let me just write it here. Which rule will explain the solubility of calcium in water? Which rule? Or calcium acetate in water? Which rule? Not 5. We're not focused on the cation. We're focused on the anion. Okay, 2 students got it. I need to make sure that the other 5 get it. So when we're trying to determine solubility, you guys, I look at my anion, which is acetate. Acetate is here. Look at rule number 3. It says any cation paired with nitrate or acetate is soluble in water. So we label it aqueous. So is calcium acetate soluble or insoluble in water? Thank you, Isaiah. It's soluble. So what do we label it? If something is soluble in water, so what are we going to label it? Thank you, Dominique. In other words, aqueous. Let's go to the other component in this reaction. Sodium carbonate. Let me write the question right here. Is sodium carbonate soluble or insoluble? In water. We look at our anion, carbonate. Carbonate is here. Look at what it says. Carbonate ion, sulfide, phosphate ion, and hydroxide ion paired with cations form solids unless the cations are from rules 1 and 2. Let's just put rules instead of groups. Which means lithium, sodium, potassium, or ammonium. I agree with Isaiah. This is soluble. So since it's soluble, what's going to be the label it has? Great, aqueous. Okay. Now, if we have two things that are aqueous, we're going to break them into ions. Okay. So again, this is old material that we have to bring back to our memory. The way that we break this into ions is that we reassign the original charges to this. So this 2 that you see here used to be the charge in calcium, Ca2+. Then there's a 1 right here in calcium, which is the charge for acetate, C2H3O2 -1. Okay. Put a 1 in the chat if breaking into ions that calcium acetate makes sense. So when I break NaCO3 into ions, what's going to be my sodium ion? How does it look like? Let's put it in the chat. Not Na3. Remember that CO3 is a polyatomic. Make sure that you review ionic compounds. Okay, you guys, remember, CO3 is a polyatomic. So this has a subscript of 1. So the sodium ion looks like Na+1. Remember that sodium lives in group 1A. So it has a charge of +1. The 2 in the bottom of sodium is the charge of the carbonate. which is CO3, 2 negative. Put a 2 in the chat. If now you may start recalling how to break things into ions. If not, make sure that you practice. Okay, in a double replacement reaction, remember that what happens is that there's a switch of partners. This calcium is now going to be paired with your carbonate. The sodium is going to be paired now with the acetate. So when I write those chemical formulas, this is how they look now. Ca2 plus, CO3, 2 negative. And then we have Na plus 1 combining with C2H3O2 negative 1. And we're going to write that chemical formula. So the chemical formula of Ca2 plus and CO3 2 minus is going to be CaCO3. The chemical formula from the new combo of ions is going to be NaC2H3O2. Let's go back to solubility rules. Going back to my solubility rules. Let me just write it in the corner. The compound that I made is CaCO3 versus NaC2H3O2. This is what we're comparing. Let me label this A. Let me label this B. Based on the solubility rules that we talked about, which one is aqueous, A or B? According to solubility rules. Great job. Exactly. Letter B. This is aqueous. What rule tells me that that is aqueous? Rule number 3. Because acetate is present, and that is always soluble in water. In addition, rule number 1, because anything that has sodium in it is aqueous. Let's look at the calcium carbonate. Is that aqueous or solid? Calcium carbonate. Great job, Isaiah. Yes. Calcium carbonate is going to be solid. The reason why this is going to be solid, okay, is because carbonate, in order to be soluble, needs to be paired with anybody in rule 1 and 2. If it's not paired with that, it's going to be a solid, okay? So in this double replacement reaction, this is a solid, this is aqueous. There is a term that we utilize in order to determine the solid in my double replacement reaction, and that is called a precipitate. So in a question for exam 4 or for the homework, if it asks you which one of the following compounds forms a precipitate or forms a solid in a double replacement reaction, for example here, your answer will be calcium carbonate. So this is where I'm going to stop lecture. when we start again and finish up chapter 8 next week, we are going to continue practicing at least one more problem of this, so you guys are ready for the chapter 8 homework, which is not due until later, but at least I want you guys to be able to understand this concept. So thank you guys so much for coming. This is all for today.